Charging battery.
Well, hello and happy Friday. Um, so I've been thinking for a while. I should probably get some sort of consistent introduction set for this. I'm I oh and don't mistake me on this. I have not done any preparation for this at all. I just think it would be a good idea. Um, but we'll just try some stuff until, until we find something that I like. But the important points right now are that hello, my name is Nathan. I am a PhD student. I'm hopefully gonna be graduating in just a few short months, and then be done my degree, which will be really lovely. Because it's been as of today about 12 years and 4 months, um, which is that's kind of a lot. It's been a long go. I went straight from doing my bachelor's degree in chemistry at the U of L, and then went straight from that into a master's degree, and then didn't even finish my master's degree. I did what's called a PhD transfer because I knew at that point that I wanted to get into teaching. And not so much the research side of it. I really like research. I want to facilitate it as best I can, but I think the best way for me to do that is by teaching and equipping other people with kind of the tools that you need to just engage in that scientific inquiry. Um, and and like that's obviously I think a really important part of the process, and it's a part of the process that I actually really enjoy, and I think I'm quite good at, because I'm perfectly good at like doing the research, and being in the lab, and you know like doing the physical research, um, and like I'm a good writer. It's it takes me a long time, and I don't really enjoy it, but I'm good at it. Um, but essentially, this boils down to I don't enjoy the research in the way that I enjoy the teaching. So really, for me, the goal is just to get a purely teaching position, whether that's an instructor. Because I mean, like realistically, most of the strictly teaching jobs at universities are not tenure track. The concept of teaching professors who do not run a research program but just teach is it's alive. I feel like it's maybe growing a little bit, but it's still quite rare. It is nigh to a unicorn sighting to actually find a tenure track teaching professorship. That being said, I applied to one on Monday, so we'll see how that goes. Wish me luck. Um, but yeah, like I've seen enough people run research labs that I know that that's something I don't want to do. Um, I think fundamentally though, like it's not the paperwork, it's not the writing grant proposals and stuff like that. I think I could deal with that, but there's two things. Um, First is that uh, pretty much every professor that I've seen who does well is a freaking workaholic. Um, the number of hours that they put in, and the extent to which they uh, just like work themselves silly, um, is not something that would be sustainable for me. It's not something that I would see as fun. Like it says, I really like what I do, but it's not my entire life. I'm a whole entire person outside of that, and I don't want to have a job that has me working that much. I put a lot of value on work-life balance these days. Uh, it's, you can talk about uh, my several years that I was burnt entirely out, and but anyways, that's for another day, I think. So that's the first thing is just the workload that I've seen, and the kind of the environment that academia creates almost enforces that sort of a work ethic, and because like the academic environments can be quite toxic, particularly in terms of stuff like that, of just like valuing productivity, sometimes to the exclusion of all else, and so yeah, it's just it's not an environment that would be enjoyable or sustainable for me to be in. So that's one reason. The other reason is that I find for me I'm genuinely not very good at asking questions, at like thinking of new research questions of like seeing the connections between certain things that other people do not see. So I've come to realize that I'm not a great question asker. Just my like it's not that I'm not a creative person. It's not that I'm like not a curious or intelligent person, but I'm very, very much an in the box thinker. I like my box. It's a comfortable place, and I'm very good at like following up, applying these rules that I've learned, these processes that I've come to understand. I'm very good at applying those. But the outside the box thinking, the coming up with new ways to do things, the letting go of the assumption that what we the way that we've done things is right and doesn't require innovation. Stuff like that is where I struggle, and so I don't see my strength as being in like driving research, and I don't want that that high commitment of a job. So really that kind of leaves me with just focusing on teaching, which is entirely fine by it. Like I'm very okay with who I am, and me being aware of my strengths and my weaknesses is nothing but good for me. And teaching just it makes the happy brain chemicals for me. It's something I really enjoy, and I absolutely like see the value in just in being a good teacher. And I've been at this for a long time. I've been teaching for just about 8 years. I've had a good couple hundred students that have passed through my labs and all that. I really like to. I get a lot of satisfaction from like seeing my students succeed, graduate, go do cool things, but also just in the in a bit of a finer, like a closer focus. I like seeing people just kind of work through problems that they're having difficulty with. I like helping them through that, and like facilitating that process. And usually this doesn't actually involve me doing a whole lot of teaching, like not necessarily like explaining a lot of concepts in depth, but really just helping students connect the dots using the basic knowledge that they already have, because chemistry is such a it's a discipline that benefits very, very heavily from procedural knowledge, from just like having an approach to questions, like understanding some basic fundamentals, and then just understanding how to apply those to different situations, and just like seeing the commonalities in these processes and the differences, and using the synthesis of those to tackle things that you maybe haven't seen before. So which is why like I tend to be very much against I'm not against memorization, because I mean memorization is the thing that is just going to happen as you get to know a subject better anyways. What I object to is the assessment of someone's capabilities in specifically in chemistry, because that's what I do. But assessing their capabilities based on their ability to memorize things. Like I've you know, naming no names, of course. I know of professors who, when they're teaching organic chemistry, for exams they don't supply like a pKa table. There's just like a table with a bunch of different example compounds, and effectively how acidic they are. And it's just dozens and dozens of compounds and just a number assigned to each of them. And so by not supplying this, they're requiring students to memorize pKa's of certain classes of compounds. Excuse me. And what an incredibly worthless thing to get them to do. What a waste of time. And also what an absolutely worthless way to try and assess how good they are at chemistry. It's mind-boggling to me that that this is a thing, because it's completely unnecessary. We've got books for that. We can print out pKa tables. We can Google them. I could find a pKa table in 10 seconds once I got a browser open. Like it's like the information is accessible. And when you're doing these things in a lab, like this is all, when you're working in a lab, you plan your steps, you plan your syntheses, you take time to think through what you're doing. I can think of a couple notable exceptions, just of certain people I've known, but we'll talk about that another time. But the point is, like, when you're in the planning phases, which is 80% of doing chemistry is just planning and reading. You always have access to a pKa table or a periodic table. So like, why on earth would I test somebody on if they can memorize the element symbols? Like, they'll pick that up as we go along. But it's not a useful measure of somebody's aptitude for chemistry in a theoretical or a practical fashion. And this is the other thing, is chemistry from a theoretical side and a practical side. They're like testing these two different kind of aspects of an education in chemistry. Exams, as they're laid out, typically, I think, they can be made in such a way that they give a good estimation of a student's theoretical understanding of how chemistry works, and that's very important. It absolutely is. And but the thing is, like, this is not the entirety of what chemistry is, and the issue with exams too is that they're like it's always a time crunch, and it is very difficult for people who don't test well, because some people just do not take exams well, because of high pressure, lots of distractions, um, and the pressure can come from multiple different sources, and so, like, it's for any of a myriad of reasons, students may just not do as well in exams as their actual skill in that environment would suggest they should, um, and on the practical side, I mean, I've met a lot of different students. I've worked with a lot of students. Like when I was in my undergrad and my graduate studies, I've met people who are straight A students, and I wouldn't trust them to hold a beaker full of water, because they're just they turn their brain off when they go in the lab. But then there's people who are solid C's in their lectures, but are some of the most skilled and conscientious workers in a laboratory setting that are come across, and I don't feel the need to watch them particularly closely. So, like, it's obviously it's not it's a very easy thing to say. Oh, exams aren't a good way to test knowledge, and so they should just be better. I don't know the answer of how we make that representative of an actual reflective of a student's actual skill, but yeah. So I don't have the answers to this. I just have objections right now. It's two entirely different tasks to recognize the issues and critique the way things are done. It's a separate thing entirely to come up with the way to do it. And I do, I obviously I have some good conceptual ideas of what I would like to do, which is effectively give so much more time than they should really need for the exam, to relieve the time pressure and require effectively no memorization on the test, but like craft the questions so that they are problem solving. They will test the understanding of students and their ability to do the written part of chemistry, or to understand the theoretical underpinnings. And oh man, you know what? One other thing that I know happens fairly frequently, that I think is one of the most nonsensical things, is having a written exam in a lab course. And like, so at the U of L, we've got, for almost all of the chemistry courses, there is an associated lab that you take at the same time as the course. It's you have effectively like 3 hours of lecture and 3 hours of lab every week. and you have to pass the lab and the lecture independently, so on and so forth. But there's a couple courses. Well, at least 3 courses that I know of, and a couple instructors that assign written exams, like a lab final, and so just exams like on the experiments that the students did, and ooh, excuse me. So, and this is heavily based on just like memorization of the lab procedures that they did. And like, yeah, they should have some passing familiarity with what they've done, but to test on that base fully on memorization is frankly absurd. And like, why on earth have a written exam for lab when you could just have a practical one? There's so many ways that you could construct that. That would make a lot more sense than a written final. Like, what an incredibly silly thing to do. The only thing I can think of is that would be like a written component of whatever final exam for lab you give. Like, have a practical component and a written component if you must. But then, like, for their written component, give them access to their lab books, because they should be keeping, proper notes as they go along, and so like, why on earth get them to memorize a whole bunch of experimental procedures and just nitpicky details about these? And again, because it's just memorization, and it has no value. Whereas like if you can test them on their ability to write helpful, like useful notes in their lab books, I actually kind of don't hate the idea of testing on that. Like, reconstruct this experiment using your own notes and nothing else. Because let me tell you, my note taking drastically improved from my third year of undergrad to my third, fourth year of grad studies, and that's fundamental skills, and I could see having some time spent on that, and some exam material based on that. Yeah, but unfortunately, nobody really asks me at the U. Not as things are right now, because I am but a lowly grad student. Really, what do I know? Yeah. Anyways, I'm good. I'm done. I think that's all about all I've got to talk about. I have run out of steam entirely. So, I'll switch to my whiteboard, and we'll do a couple little chemistry questions. So last week, by which I mean Tuesday, because that's when this was. So we talked a little bit more about naming hydrocarbons. It's going over the method for that, assigning the longest carbon chain, so being the principal carbon chain, and then identifying substituents and what carbons they're attached to. And then we did that process in reverse, going from the name of the compound to the drawn out molecule, to the Lewis structures. Here, these are not Lewis structures. These are line structures, line diagrams. It's those things, the squigglies. This, if anything, is easier than going from structure to name. And again, it's just identifying the principal carbon chain, like decane being a 10 carbon chain, And then just piecing together what each of these substituents are, like 6-isopropyl or 3,7-diethyl, and then just putting them on the carbons that they're associated with. And so that part's super easy. And then we got into this stuff, which was not associated with the questions here, but this was just because of some questions that I got from one of my lovely viewers. And we just got talking about a couple different things, just about dynamic equilibria, which is when there's two reactions that are happening, A plus B creating C plus D, and also C plus D creating A plus B, but they're happening at different rates. And so there is, they arrive at an equilibrium that is skewed towards the production of C and D, and this is kind of an energy diagram that corresponds to that. So we just went over a bit of just some terminology like this is the activation energy, the energy input into the system that needs to occur before it can fully react, because when the energy is increasing, you've got bonds breaking, you've got molecules coming further apart than their ideal, or closer together than their ideal. Both of those things raise the energy of the system, and then when you come down in energy, the decrease in energy is like bonds forming, atoms settling into their kind of ideal distances from each other, so on and so forth. And yeah, then over here we were talking about drying agents for organic solvents, mostly, and what those do, and how they'll just aggressively react with water to remove it from the organic solvents, because water in your solvents can really mess stuff up in the kind of chemistry that I do. So we take pains to exclude that, and the drying agents we use often create hydrogen gas and a lot of heat, which is not a great mix. Something over humanity. Yeah, so it was just a bit of a tangent that we went on there. It was good fun. That led to the story of how I made a flask into a flamethrower, which was a really, really good time. Really enjoyed it. Don't try it. Yeah. I was going to say something else about that, but I forgot what it was. So, no worries. Alright. So, this question is dealing with: in each compound below, classify the indicated carbon as primary, secondary, tertiary, quaternary, or none of the above. So, first we're going to define what that is, and this is not related. Okay. So, primary. So let's define our terms: primary, secondary, tertiary, quaternary, or none of the above. Okay. I am going to abbreviate these because it just kind of takes a while to write things with a mouse, and I find it annoying. So, dirt. Quat. I'm not going to define none of the above for hopefully obvious reasons. So primary. This is often denoted as first degree. And what that means is that you've got a carbon that is attached to one other carbon group. So actually, instead of R, I'm just going to say C prime, just to distinguish it from this central carbon. because the label of primary applies to this carbon. Because this carbon is attached to one other carbon and three things that are not carbon. These don't have to be hydrogens. They could be things like, let's just call you bromine. So yeah, it's attached to three things that are not carbon and one thing that is carbon. So it is first degree is primary. Secondary is denoted second degree. And that's going to look like H. Just call it another H. C prime. C prime prime. Alright, so this carbon in this diagram is secondary because it is connected to two different two carbons and two things that are not carbon. So yeah, and now you may be suspecting that tertiary follows this trend, and you would be right. So it is a third degree or tertiary, and just means that this carbon is connected to three other carbons, and sure, let's just call it OH. So this this molecule is actually well, hold on. Let's finish drawing the stuff on the molecule so we don't look silly. Okay, so three methyl groups attached to a central carbon, which is attached to a hydroxyl group. That is T-butanol. So you may remember, but probably don't, that somewhere over here. Aha, yes, very good. So we were talking about the different ways to classify butyl groups, like as at the time we were talking about like as substituents attached to other things. So we went through isobutyl, sec-butyl or secondary butyl, and we went over T-butyl, which is this this carbon that is, let's use a better color. So this carbon attached to 1, 2, 3 other carbons and something else. So this is a third degree or tertiary carbon. And so when we go down to, where on earth are we? There. Okay, not as far away as I thought. So yeah, when we've got that basic structure, then the R group up there is a hydroxyl group or an alcohol. Then this becomes T-butanol, tertiary butanol, because this is a T-butyl group. All right, and a quaternary carbon is a fourth degree. It's not often it's like not a term that's used particularly often, mostly because interesting things don't usually happen at quaternary carbons, because there's no polarity to the bonds. So there's no like no particular like deficiency or excess of electrons around it. So it's kind of just boring. Yeah, like just nothing really tends to happen at quaternary carbons. They can be important, mostly in identifying compounds, because we've got spectroscopic methods, like ways to characterize these, like carbon NMR, And if you do a DEPT or a depth scan of this, it's just a different technique that you use in carbon NMR that changes the orientation of the carbon signals based on how many hydrogens are attached to that carbon, and so you'll have I think it's odd numbered, like carbons attached to 1 hydrogen and 3 hydrogens face up like normal. Carbons with 2 and 4 hydrogen, well, 4 is not likely because that's just methane. You're not likely to get a carbon NMR of that unless it's very, very cold. Anyways, not important. Those are pointing down. And then quaternary carbons like this one don't appear at all. So they can be useful in some kind of niche circumstances, but mostly they're just hanging out, just being a little guy. So yeah, quaternary carbon, fourth degree carbon it's a carbon connected to 4 other carbons, and that's it. That's the whole thing. Okay, so now that we've got our definitions. Okay, so this one, I'm just going to draw this molecule out fully. See, make this bond angle a little better so it corresponds. Carbon. Okay, not going to bother writing out all the hydrogens because, again, I'm on a mouse and it's slow. So we're looking at this carbon because that's the one that corresponds to the drawing. And this carbon is attached to 2 hydrogens and 2 carbons, which means that it is secondary. All right. And okay, so the difference between this molecule and this one is that in this one they have drawn the hydrogens. There is nothing else different about this. It is exactly the same molecule in every way. So I'm not going to bother drawing this out again because I've already done so. That is also a secondary carbon. Now this one, okay, let's just draw it out. Okay, going to draw out the carbons that are around the carbon of interest. And then just draw out any hydrogens that are just not shown, because this is an important thing about line structures. It's something that I see my students in tutoring lab, or I've seen a lot of students just get caught up on this because they just forget that there's hydrogen attached because it's not drawn. And so it's which I mean, like, it's an easy thing to forget because out of sight, out of mind, and all that. But it is an extremely important thing to keep in mind whenever you're doing whenever you're drawing out compounds, because like everybody uses line structures like this because it's convenient and it's fast. And once you once you are very well versed in this stuff, then it becomes really quick, very easy. Like I look at this carbon here, and I don't have to think about it. I know that there's a hydrogen attached to that because I've seen this, a million times. so in any circumstance where you're and this is something that I say for organic chem in general. It says if you get stuck or if you're not sure what to do, draw stuff. And what I mean by that is draw out all of the atoms around what you're doing explicitly. If it helps, draw out every single atom on this molecule along with all of the hydrogens. And so the way, just as a very quick primer, if you haven't run across this before, so line structures, every vertex of the line structure is a carbon atom. And every carbon atom needs 4 bonds to it. No more, no less, unless you specify otherwise. But like, if it's anything else, you have to specify it. And there are circumstances where you can do that, but I'm not going to get into that right now. So, every carbon needs 4 bonds. And so when you count up the bonds around this carbon, you got a single bond here, here, and here, so it's 3 bonds. And those are all attached to carbons, but 3 bonds is not 4, unless I very much miss my guess. And so implied in this structure is that there is a hydrogen attached to this carbon as well. It's just not drawn. Hello, Tien. So yeah, and for that's how we did over here as well. So this carbon is attached to 2 other carbons, and that is a grand total of 2 bonds. There's 2 single bonds there, so it needed 2 more bonds that must then be to hydrogen. If it's connected to anything except hydrogen, you must draw the bond. If there's an alcohol, if it's connected to an oxygen, you have to draw that explicitly. And you can't just leave it as just a line, because that's reserved exclusively for carbons. So it's just, if you can count to 4, you can do like 90% of organic chemistry. Okay, so in terms of this one is a little bit tougher. I mean, just one moment to pull something up. Sorry, one might be. Yeah. Okay. All right. So I probably should explain what I'm doing instead of just not talking to you. So I was looking up the answer sheet for this set of questions, just because I wanted to see what they said about this carbon, because there's a couple ways that I could see doing it, but I think their way is good, and so I'm going to stick with that. Jesus So Cakes, hello, good to see ya. All right. So for this carbon, now there's 2 bonds over here, a double bond, and there's a single bond to another carbon over here, which means that there's 1 bond missing, and that is to a hydrogen. But this does not fit the definition of primary, secondary, tertiary, or quaternary, because that is specifically for tetrahedral carbons, which is, say, carbons that have 4 single bonds to them. So it's, well, I object very slightly to their system, but in the way that we use primary, secondary, tertiary, quaternary, it kind of makes sense. I think there's better ways to do it, um, but like how I would classify this though is um, vinyl. So their answer is none of the above. But this is a vinyl carbon, which is a carbon that is part of a double bond to another carbon. And so this changes several key properties, which is why I don't mind them saying it's not, it's not a secondary or a tertiary, because those don't really make sense in this context. So I do agree with that, but and I guess technically that does make this none of the above, but I do like this. I prefer to call this a vinyl carbon because there's other ways you can use that in organic chemistry as well. To be one of the four, would there have to be a bond or line coming from each corner? Yes. Yeah. So when I say that this classification only applies to tetrahedral carbons, what I mean is that that it has to be a carbon with four single bonds to it. This is not the best way. Representing this on a two-dimensional surface is kind of difficult. So if you can imagine like these lines being in the plane of the monitor, this one on the dashed bond being pointed kind of in that direction but directly away from you, and the wedge bond conversely being coming towards you out of the monitor. I'm gonna go grab my model kit and bring that over here to show you. I'll be right back. Alright, I got me my busted old molecular modeling kit. This was my partner's before me, and then it got me through my undergrad as well. So it owes us nothing. Like arrows on a map or a 3D map. Yeah, kinda. Yeah, absolutely. So in a molecular model kit, I'll try to hold this up so you can see. So this is a tetrahedral carbon. So it's got these four different kind of spikes coming out of the central point. So the central part here would be the carbon, and then the spikes coming out of it are the bonds. So that's the kind of shape that we're talking about here, and I think I'm going to leave like the big geometry discussion for another time because I just don't feel like it right now. Are all the lines coming out hydrogen? It depends. So on so for line structures, so line structures are basically a chemistry shorthand for hydrocarbon compounds. So it's used very, very heavily in all of organic chemistry. It's completely ubiquitous, and the idea is that for any structure like this, so each end of a line or each vertex of two lines or of multiple lines coming together, each of those is a carbon. So the end of each and every stick, each and every bond, if nothing is drawn here, then the atoms on either side of this bond are a carbon. Hello, Daph. How are you? Do you want to play with some carbon? Yeah. Oh, you're so cute. Oh, crunchy, munchy carbon. Yes. Oh, delicious. Oh, very good. Adorable. Carbon cat, yes. Yeah, so on the lines, there's a carbon at every point. So I'll draw these out fully over here. Why did I do 5 of these? It takes so long. So every point on the line, the end of a line or the vertex of lines. I'm gonna make more. Ha! Yay! There we go. So all of those are carbons, and now the cardinal rule here is that every. You're so funny. Sorry. She's very cute and very distracting. So the cardinal rule for just kind of organic chemistry in general is carbons will have 4 bonds to them. No more, no less. Yes, there are exceptions, but this is one place where it's actually really good at following the rules. Carbons need 4 bonds, and so whenever something is like whenever one of the carbons in the line structure does not have 4 bonds to it, the rule is, the implication is that it still has 4 bonds, but every bond that's not drawn is to a hydrogen. So for this structure on the left, this terminal carbon here has 1 bond to another carbon, but 1 is less than 4. I've gone to school long enough to know that. So you have to, if you're going to draw out every atom, then you have to give carbon 4 bonds. And if only one of them is written here, which is a carbon-carbon bond, every other bond to that carbon is assumed to be hydrogen. So this terminal one is just a terminal methyl group, so it has 3 hydrogens to it. This carbon in the center here has 1, 2, 3 single bonds to carbons, but 3 is also less than 4, so we have to put 1 more bond in there to a hydrogen. And then this one has 1, 2 single bonds to carbon, so it must have 2 more bonds to it that end in hydrogen, and similarly for the others. Oh, that's not nice. There we go. Very, very good. Okay, so that is how we line structure. Yeah, anything that is not carbon or hydrogen must always be explicitly drawn in. So if there's an oxygen over here with a hydrogen, well, let's start here though. Start with if there's an oxygen here, you have to draw a line to it because there's a bond between the carbon and the oxygen, and then you have to put the oxygen. You must label that as O, because it's the only thing that is ever assumed in line structures is the carbons being on the lines and the hydrogens. Like if nothing else is drawn, assume everything else is hydrogen. But we don't assume anything for any other atoms. Everything else must be made explicit, including hydrogens that are attached to oxygens. You can't assume that there's a hydrogen there, because there might not be. Maybe this is a carbonyl with a double bond to the oxygen. It's not clear in the notation unless you draw that hydrogen in there. Alright. So, 4% of got about 40% of that, but try and practice a bit. Awesome. Hey, if you got 40%, like hey, that's awesome. Like it says, this stuff takes time. Always, always, always. So, yeah, no worries there. Oh, I'm glad you're back, cause I want to say from the last time I made a comment that where I said like I'm always willing to defer to people who have greater expertise than mine on a certain subject, which is true. This is generally if I'm talking to somebody who is more experienced in something than I am, I'll assume that they're correct, and I'm not. But first of all, not always, because like even in discussions with my professor about the thing that he's been doing since before I was born. Could you? That's my tea. Can you not? I have argued against some things that he said, and yeah, occasionally turned out to be right. But really saying that I always defer to people with greater expertise. That's a bit of a fallacy that I don't want to go down. It's a kind of the fallacy of an appeal to authority. And so, like, while yes, generally I will defer, or like accept when I'm told that I'm wrong by somebody who just knows better. That's not the entirety of it, because I am always willing to be corrected and to be shown that I'm wrong by anybody. If anybody can show me I'm wrong, I will absolutely accept that. Hello, Sensation Black. Nice to see you. Trying to keep the cat out of the tea. Good luck with that. Yeah, it's a losing battle. That is for sure. But yeah, we do our best. Wait, I forgot the name, but it's the appeal to authority fallacy, right? Just read something like that, so it's like an Easter egg. Yeah, actually, it is. Yeah, that's exactly it. The appeal to authority. Now it's cats love them some tannins. Yeah, absolutely. Don't we all? Yeah, so like a appeal to authority is a fallacy in like argumentation and debate, and get you greatly admire the willingness to stop lying conform. Yeah, absolutely. Like it's a part of just like applying critical thinking, just uniformly to all aspects of well, everything. We should always critically analyze information that's given to us. We shouldn't believe things for bad reasons, and an appeal to authority is it's not a sufficiently good reason to believe things sometimes, and so it's always good to think about those things and just investigate and look for evidence, because we are scientists and skeptics, and so we do not follow people, like we don't put our we don't put our belief into individuals, even if they are incredibly smart people. A great example of this is Linus Pauling, because it's also the people who can be put in authority positions could be put there through subjective or unethical means. Absolutely, I couldn't have said that better. Dr. Phil is also a very good example of this. Absolutely. Yeah, someone who's just like, like calls himself doctor, but like, yeah, so like Linus Pauling, huge name in chemistry, like won multiple Nobel Prizes, I believe. Linus Pauling, I'll put that in the chat. So yeah, made enormous, incredibly valuable contributions to chemistry, and like should absolutely be lauded for that, but indeed, but also like even then we don't take everything that they say as gospel truth, because he was a big proponent of saying like these, like taking mega doses of vitamin C, something great health benefits, kill a common cold, blah blah blah. None of which is true. There's absolutely no evidentiary backing that taking massive doses of vitamin C is doing anything except making your pee expensive. Because like it's many of the vitamins, well, pretty much all the vitamins that we take, they are like it is very important to have these vitamins, and if you're deficient in them, you'll notice. But having an excess of them, they just get eliminated, they don't do much of anything. So even people who are among the smartest people in the world can believe things for bad reasons, and so we always have to be we always have to be kind of critical of others and absolutely of ourselves as well. It's counterintuitive to me because I grew up with vitamin C for colds. Yeah, hey, same. And if I'm not mistaken, there is some evidence that vitamin having significant amounts of vitamin C can slightly lessen some symptoms of colds. But honestly, I'm highly skeptical that it does anything whatsoever. Again, it's important to have enough vitamin C, but having an excess, I don't really think there's any benefit there. But thank you, I'm glad. but yeah, no. So it's because like I certainly I've talked to a number of people, because like I mentioned last time, I grew up in a very conservative religious environment where some of the arguments that were made against scientists was well, they're just believing everything that they're told, which can be a valid criticism, because there's lots of cases where we just believe things that we're told, because I mean it's not pragmatic to just research in depth everything that you come across in a day. So you're just going to believe some things that you're told because who's got the time for that? But it's I think it's not at all correct to say that to equivocate quote unquote believing in science versus believing in anything something else, because science is based on evidence. It is and specifically on like the discourse of scientists, and like who can make the best case, who can make the most consistent one with the least exceptions. Reminds me of one thing Nietzsche said, that science will become the new Christianity, or will partially. I really wish I had read up more on Nietzsche. My partner has several books of Nietzsche's on the shelf. I just have not managed to get around to it. I'm very interested in philosophy and different people's takes on it. Right? Yeah, they're the best. Yeah, like I'm always very down to talk about philosophy, but sometimes the amount that I've read is actually quite small. I mostly just listen to some podcasts and just yeah. So definitely something I want to get more into. But what was I saying? Right, about yeah. So like I've talked to some people who distrust science because largely because they don't understand it. Yeah, fair. And like because there's this big misconception that of just fundamentally what science is. Some people would think that like science is just this collection of facts. It's the things that are written down in textbooks that people memorize and then spit out on tests in exchange for an expensive piece of paper. But that's not at all what science is. Science is not a collection of facts. Science is a process. And it is a process that is actively seeking to prove itself wrong. And whenever it finds something that was accepted, that can be proven wrong, it abandons that, because it always aims to have the most correct view of the world, the most correct understanding of the world based on the available evidence, and so it is a process that self-corrects, and that if one is to like follow the for lack of a better word, the tenets of science, this willingness to be corrected, this just as willingness to admit that you don't know everything, is extremely important. So it's always approaching problems with humility and understanding that, like, you might be proven wrong, you might have a misconception, and understanding that you have a misconception is a wonderful thing, because then you can correct that. I've always thought of science being kind of like an image that is increasing in pixel clarity as time passes. I love that, actually. I really, really, really like that. Because like things like, just take our understanding of gravity, for example. In Newtonian physics, we have like this really, really good jump in like understanding of what gravity is, and it was even used to minor imbibe increasing quantity of dihydrogen monoxide. I shall do so. I appreciate the reminder. Being wrong is such a great feeling, even if being right is a great feeling. Absolutely. Well, I think I may very slightly disagree on that. Because, I don't know if anybody likes being wrong. I don't feel good when I'm wrong, but I feel better when I correct myself. And so, I definitely think we're getting at the same thing. But yeah, it's just when you're focused on when you're focused on the goal of believing as many true things as possible and disbelieving as many false things as possible, then the act of correction is that is the goal. And I like that is what makes the happy brain chemicals. That is the good feeling. And so that really mitigates how bad it feels to be wrong, to the point that it's like, yeah, I might be wrong. I will probably say totally incorrect things on this stream, because I am very much still learning. That's true. I find most self-reflection failure. If you get to rebuild yourself with strong material, 100%. I completely agree with that. And yeah, just like taking that intellectually honest approach, and not resisting it when you're shown to be wrong. Like that's a great thing. That is the mark of a good scientist. Because we should always be trying to hold the most correct view of the world possible. And now I'm just remembering that so your idea of science being like an image that increases in clarity as we go forward. I love that, and like here's an example of why. It's like Newtonian physics comes along, and like gravity particularly, and now we can explain so many things. We can explain the parabolic shapes of objects that are thrown. We can describe how the moon orbits Earth, how Earth orbits the sun, how like all these big massive things we can now explain with gravity, and so that paints this picture that is completely different from everything that came before. And now is a more complete picture of what nature is actually doing. But then like it's still a little pixely in some areas, and so like the orbit of Mercury is one where like Newtonian physics doesn't perfectly explain the the orbit of Mercury, and there's some other issues you get at larger scales, and then Einstein comes along with the theory of his theories of relativity, and so this provides a new way to look at gravity and new mathematical ways to describe it, um, and this lets us like now perfectly calculate the orbit of Mercury, and also explain things like gravitational lensing around the sun, which was this was a big thing. Was in 1909, early 20th century, a few years after Einstein releases the publishes the theory of relativity. They do a test during a total solar eclipse where the sun is blocked out, and now we can see some starlight from behind the sun that is like curved around it, and prove the theory. Make one proof of the theory of relativity, and so this idea of like increasing the resolution of these areas of the painting that or of the image that Newton didn't quite fully explain. Because we didn't throw out the entirety of Newtonian physics. Still very useful. And sensational talking about like Newtonian physics won't work on a planetary scale due to mass and speed. Partially true. It works for a lot of like a lot of orbital mechanics, as far as I'm aware. Like the orbits that are further away from the sun, because they're at a lower velocity, they kind of fall into the regime of being well understood by Newtonian physics. But certainly there's lots of cases out there in other things that we've seen, like around Sagittarius A star, our black hole in the Milky Way. There's stars orbiting that black hole that Newtonian physics just loses its mind over. But even like we were talking about, like the orbit of Mercury is not perfectly explained by it. So yeah, like it's gotten much better with Einstein's theory, and it's gotten to be a much more clear picture. And now now we're finding other little corners of it that are still kind of pixely, but like we haven't changed the image entirely. We've just made parts of it better, so it's more complete. Can't say on advanced physics like gravity or force, but I will say it's eye-opening just thinking about things like torque and the idea I can figure out the numerical aspect of it. Absolutely. I love physics. For just reasons like that. Torque is definitely one that threw me for a loop, and tension, tension in a wire is just wild, absolutely wild. Very firm understanding. Oh, don't worry about it. Like I would not describe my understanding of physics as firm either, so don't you worry. We're all learning and we're all getting there. But the entire endeavor of science is just this iterative process that just slowly corrects itself and just becomes more precise and more generally descriptive. Gyroscopic precession too is still a pain in the tailbone. Absolutely, I've had to learn a little bit about that, like conceptually, not really heavily mathematically, but for understanding some things like NMR spectroscopy in chemistry, like nuclear magnetic. Nice try. Let's do it again. Nuclear magnetic resonance spectroscopy. Very, very closely related to MRIs. They work on the same fundamental principles. Things like electron paramagnetic resonance spectroscopy, similar again. So I've had to understand. I've had to learn some conceptual bits about precessions and like how magnetic fields align and interact. But it's a whole thing. Yeah. Need some dihydrogen monoxide. Cool. Yeah, no, absolutely. Oh, it's very, very cool. Okay, I'm going to take a little rabbit trail here, and oh my goodness, where have I not rabbit trailed so far? Okay, let's go up here. Okay. All right. Very, very brief, very basic primer on what nuclear magnetic resonance spectroscopy is and how it works. I am going to barely scratch the surface, and we just kind of have to be okay with that. So NMR. So this operates on the principle that the nuclei in atoms all have a property called spin. Now, this is not a physical spin as we would like. It's not like you take a ball and spin it. It's not like that. It is not a physical spinning process. This is a quantum effect to do with the how do I describe this? Like with the this is a problem when I do not thoroughly understand this. I just need to think about what I have to say for a moment. Yeah, so nuclear spin is, again, not a physical process, but something that's like descriptive of how the wave function kind of iterates itself over time, and it's like, I don't know. I'm gonna move on because I think I have gone past the edge of my understanding here, and generally best to shut up when you do that. So, but the important thing here is that nuclei have magnetic fields, small ones, really little ones, but they exist. And if you things. It's just, yeah. Like I said, I promise I won't know everything off the top of my head. So when I get distracted and start talking about something, yeah. But so nuclei have a magnetic field, albeit a very small one, and because they've got a magnetic field, they can interact with other magnetic fields, and so in an NMR. So it's basically just like a big box. Everything is slightly magnetic, or are they only magnetic because of nuclei? So they didn't have one, they would be magnetic. Okay, so this is going to be a big discussion. Okay, so everything can fundamentally be like all matter can fundamentally be induced to have a magnet or to respond to a magnetic field. So a hesitant yes, but like the great emphasis on the slightly part of it, because most compounds are diamagnetic, which is to say for every electron that has spin up, which is what these arrows for electrons denote. So spin up and spin down. Almost all electrons are paired, and when they're paired, it is called a diamagnetic compound or a diamagnetic material. And so because it's not just nuclei, because electrons have spin as well and a magnetic field as well. And actually, electrons tend to have a much stronger magnetic field than nuclei do. Um, but there's plenty of cases where you can have unpaired electrons. This is something that I specialize in with some of my compounds, which is how we do EPR spectroscopy, but that's for another day. So any material that has an at least one unpaired electron is called paramagnetic. And those are generally far more susceptible to magnetic fields. Those like things like like fridge magnets will stick onto a fridge because there's some metal in the fridge that is paramagnetic, and so when it is in the presence of that external magnetic field, the fridge magnet, then it aligns all these paramagnetic spins and they just come together. Is light magnetic or has no mass? So it has speed. So, oh boy. Okay, so we are getting. Okay, so light is carried by photons. So photons are effectively like particles of light, and photons are force carriers in the electromagnetic field. So like light is electromagnetic radiation, which is carried by photons, and kind of. It's magnetic. It's electromagnetic. The fact that it has no mass is not actually an issue. And yes, it does have speed. So yeah, light is like vibrations through the electromagnetic field. And but photons don't generally interact with other photons, so like you don't like bend light with a magnetic field. Yeah, so to be affected by a magnetic field and like manipulated by a magnetic field, there has to be a charge or a dipole, and a dipole being just like a like charge separation, basically. So basically, you need to have an electric charge to be manipulated by a magnetic field. It's how things like mass specs work. Where do electric currents come from? Several sources. So you can make them. You can make electric currents by like just using strictly electrical potential, like through wires. In our power grid, we just kind of like shuffle electrons along the wires, and it is this. There's a specific word for it. Not induction, but impulse, I think. It's like when you get all the electrons in a line just kind of shuffling a little bit in one direction, then it creates this electrical. It creates an electrical current, and that can interact with a magnetic field, which is how motors work. So you have the interchange between magnetic energy and electrical energy, and you can induce magnetic fields by running current through like copper wire. Like this is an electromagnet. You run a current through copper wire, and it produces this unified magnetic field. But oh boy, I'm getting I'm getting whelmed, not overwhelmed by like just all the stuff from physics like 10 years ago that I haven't thought of in forever. Um, but yeah, like this is a way to um, and like it can absolutely work the other way too, because like a lot of motors will be just like magnets that are spun around a a wire, a conductor, and that magnetic induction from that causes an electrical current. And vice versa, and then you get Lenz's law that acts against all the, and then you get heat, and it just has, there's, this, huh, this gets to be a lot. My brain is my brain is starting to not work. um, okay, so I think I'm starting to do a bad job of explaining things. um, but my brain's frying. Yeah. Fair enough. I'm there with you. I think I'll probably have to call it quits. I have been on here for an hour and a half now, and yeah. Let's see. I'll try to at least pick something that you guys said and just like explain one more thing. But I'm definitely like starting to talk about things that I don't super know well enough to make it make sense. Because like it's I don't remember who said it. I don't know if I ever knew who said it. But it's like if you really understand something, you should be able to explain it to a 5-year-old. And largely, I think that is a really really good and really accurate sentiment. And like a lot of chemistry, I think I probably could explain it at least to a certain degree. Well, I mean, I have explained it to kids because like I've worked with Let's Talk Science. Like I've taught kids in grade 2. But yeah, so but like the less you understand something, the less you're going to be able to explain it in simple terms. Because like I try my best to steer away from jargon, like technical terms when I'm teaching, and I'm much more able to do that when I like thoroughly understand a subject, but a little bit then not at all. Hell yeah! And I'm always like really excited to talk about this stuff, even if I don't know it super well. Like I'm always into like having the discussion. But at some point, I'm going to declare, hey, I actually don't super know what I'm talking about here, so take everything with about a pound of salt. Yeah. Okay, so I think what I'm going to do is I will do my best to, hell yeah, very briefly and very surface level explain NMR, and then we'll call it good for a day. So the important thing with NMR is that nuclei have magnetic fields. Very small, but they exist. And when so when you put them into an NMR, you've got this little tube that you put your sample into, and you put it basically inside of a box, a very, very, very cold box. That's got like, so this jacket of, whatever. We're just gonna leave. That's good. So this is helium. So it's surrounded by liquid helium. So it gets it down to. Sorry, it's not the sample that's being cooled to liquid helium temperatures because I'm drawing things in the wrong order. But okay, let's. Okay, there we go. This is going to make sense in a second. So you put your sample into the little tube inside the machine, and this goes into these coils. And I'll explain what those are for in a minute, but these are all inside of this big electromagnet, and that is the electromagnet is what is surrounded by the liquid helium. So it's at about I think about 4 degrees Kelvin, which is like 4 degrees above absolute zero. So pretty chilly. And at that temperature, copper becomes a superconductor, and so the current can flow through the copper with zero resistance. And so when you like when they're setting up the NMR machine, they will take a gigantic power converter and charge the electromagnet with a certain amount of current, and it's extremely cold, so it is superconducting. So this current is just flowing through the wires continuously with no energy loss. And so when that's happening, when there's a certain amount of current flowing, there's a certain magnetic field strength that is produced. And so the magnetic field is oriented up or down. It doesn't super matter, but like let's just say up. And so that is usually denoted by the just normal letter B. So magnetic field is going in this direction, and you put your sample into the machine. And is there no energy loss, negligible energy loss, because it's like a purely elastic collision? It's not actually a collision. So like if it was a collision, it would be an elastic one. But this is just current flowing with zero resistance. So there's and resistance is basically just like energy lost to like an electron that is just flowing over like like if there's all these atoms of the metal, like these electrons are kind of flowing along the surface of it, and as they do that, might get dragged a little bit back, might get repelled a little bit by other electrons, might just get like pulled on by some nucleus with a positive charge, kind of like friction. Yeah, it's similar and different, but it has basically the same effect as friction. And so when a current is flowing through a wire, it's causing something like friction, at least an analog of friction, and this causes heat to build up and causes the current to be reduced. But in a superconductor, there is zero resistance, so there's no heat loss, there's no energy loss to heat, so there's no reduction in current. And so the magnetic field inside of the NMR, that B term, is constant. And so when nuclei are put into this magnetic field, it becomes energetically favorable for them to align with the magnetic field. So I'll put it like this. So in the wild, in the absence of an external magnetic field, so like if these things are not inside of an NMR machine with a really strong magnetic field, you'll find nuclei that are spin up. You'll find nuclei that are spin down. They'll be basically the magnetic fields of all these individual atoms will be randomly oriented, and so like it'll have overall no magnetic field because they're all just in random directions and canceling each other out. But when you put these things into so that's the case when there is no external magnetic field. But when there is an external magnetic field, then there's an energy difference between spin up and spin down. Okay. Also, I'm depicting these as electrons because I don't know how nuclei are supposed to be represented here, so I'm just kind of putting arrows pointing up and arrows pointing down to represent the two different kind of like spin states, those spin states correspond to like the direction that the magnetic field of the nucleus is pointing. And so if we say there's like just a second, let me make things less dumb. Okay, so when the nuclei are randomly oriented, they're all at the same energy, which is why they're randomly oriented, because there is no energy preference for any particular orientation. But that changes when you're in a magnetic field, because now if the magnetic field is going this way, then it is a lower energy state to be aligned with the magnetic field, because it's just kind of going with the flow. When you have iron filings, and you put a magnet up beneath them, they'll all line up with the magnetic field. I forgot what it's called, but does that mean that the phenomena where if an electron changes spin or spins a certain way, another electron in the universe changes spin or spins a different way because of magnetism? That I think is conflating a couple different ideas, because that seems to touch on like quantum entanglement, where like two atoms or two particles will become entangled, and so their information, including their spin, is kind of linked to each other. And so if one changes, then, or if you measure one, then you automatically like know what the other state is in as well. And that gets weird and well beyond my understanding. But electrons can change spin. It can be difficult, but like that's we get into issues of so like they do affect each other, though, like when they're in proximity to each other is the important thing, because this is a very, very local effect, but like certainly it'll affect the electrons around them, and yeah, so there's definitely like it's like it's not like you're saying anything that's wrong. It's just it's see, I think entanglement and electron spin are not super closely linked most of the time, I think. But yeah, I super don't understand entanglement to any great degree. So yeah, would enjoy learning more about that at some point. But no, never came up in my curriculum, which is sad. But okay, so yes, pretty much same. Yeah, there's very little I can say on that and be confident. So yeah, in the presence of an external magnetic field, it becomes a lower energy state to be aligned with the magnetic field, and it is a higher energy state to be anti-aligned to that magnetic field. So think of it like the electron energy levels in a hydrogen atom. Like it's got the ground state and then it's got excited states. And that's not terribly different from what's happening here, except that here we're kind of creating the different energy levels based on the magnetic field that we're exposing this to. And actually operates really, really similarly to that in a couple ways. And so I'll get to that. So what I'm going to try here is, like, if we put this on kind of like on a graph, and we have increasing magnetic field on the x-axis, that is what we're seeing here. So if we have no magnetic field, then all of these nuclear spins all the spins of the nuclei are at the same energy no matter what orientation they're in. But as you apply stronger and stronger magnetic fields, you increase this energy gap between these two states, the aligned and the anti-aligned. And just like electron energy levels in the hydrogen atom that we talked about, the nuclei can be excited into the higher energy state, and that is an effect of these coils that we went over that I drew earlier and then said nothing about. So those coils emit radio frequency waves, so really really low energy waves. But those energy levels correspond to the difference in energy between the aligned and the anti-aligned states. So just like shining light on hydrogen atoms to excite electrons, we can shine a different kind of light, radio, light, electromagnetic radiation in the radio part of the spectrum instead of the visible or the ultraviolet, and so we can excite these nuclei to the higher energy state. And so basically there we go. They'll flip their spin by being excited, and then after that they will relax back into the aligned state. And so one way that this was explained to me, which was helpful, is that over here we've got the nucleus, and so this comes with a bit of a caveat that I said before that the spin of the nucleus is not a physical phenomenon, and that's true. But this diagram is specifically talking about is like the alignment of the magnetic field of this nucleus. And so in the magnetic field, and again with the magnetic field going in this direction, overdosing on vitamin and gradually urinating it out. That's I mean, I don't hate that. Actually, I think that could be a really good analogy. I love how weird that analogy is. So yeah, if you think about it, so right, okay, I'm just very briefly going to get distracted by this and say okay, hydrogen electron energy levels. We can excite it into the higher energy level by overdosing on a vitamin, and then most of the time it'll just come right back, and so you're urinating it out and just getting rid of it. But keep in mind that even when you overdose on a vitamin, some of it gets used, and so there's other ways for electrons to jump back to the ground state, to its low energy state. It can jump directly back, and then it'll just emit a photon of light at the same frequency that excited it in the first place. But there's also different things that it can do to relax back into that lower energy state. So if it's in the high energy state up here, then there can be vibrational states. Vibrational states. And so basically the energy that was absorbed by that atom that excited the electron into that higher energy state, that energy can be dissipated by just changing how that atom is moving in space. So it can accelerate the entire atom. It can if it's part of a molecule, it can vibrate along the bonds and get its wiggles out that way, and all of that can put this electron into a lower energy state, and then sometimes instead of jumping directly from state one to state two to state one, it can go to from this vibrational state down to here. So like exercising, yeah, kind of, or like somebody who's like really neurodivergent, like I don't know, hello, it's me, just like getting a little too much energy in, and then just like sometimes I'll just do a little bit of this and do some stimming, do some stuff with my fingers, get some wiggles out, and that's how I get a bit of excess energy out. So yes, absolutely, yeah, I have lots of good, lovely stims. Mostly I just do like I do a lot of tapping. I do some spinning, especially when I'm in my lovely chair and I can just spin really nicely. Sometimes I'll have verbal stims. And so there's all these different ways to release a little bit of energy and then have this gradual relaxation into the low energy state. Oh, and actually this brings up a really good... Okay, rein it in, Nathan. We can do this. So the difference between things that are fluorescent versus things that are phosphorescent. So like things that glow in the dark. Air guitar or polyrhythm taps. I love that. What a great way to stim and get some energy out. That's great. What was I talking about? I completely forgot what I was saying, but that's okay. Yeah. Right, fluorescence and phosphorescence. Yes. So, if you've ever been to a... okay. So, couple terms here. So we can have... we can have things that are fluorescent, and we can have things that are phosphorus. Oh, God. My writing is extremely messy today. Okay, that's fine. Okay, so two categories of things. Things that are fluorescent and things that are phosphorescent. Here's some examples. For something that's fluorescent, if you've ever been to like a bowling alley where they turn on the black lights at some point in the day, usually in the evening. So black lights just emit like a fairly substantial portion of the ultraviolet spectrum, and it causes things like cotton to fluoresce, or things like blood or other bodily fluids. Generally, things that are high in proteins. So actually is a little bit of organic chemistry in those, but lots of things fluoresce, not just organic compounds. But fluorescence is a very fast process. Where we work with protein powder, I don't know. Try it and let me know. There's usually a lot of other stuff in protein powder that might dampen or completely obscure this effect. So I'm not sure if that would work or not. But definitely worth a try. But yeah, but the big thing is fluorescence is a fast process, and it can go through some vibrational states, but generally, because like you'll be absorbing ultraviolet light and emitting visible light, so it has reduced in energy somewhat, so it's gone to a lower energy level before it fully relaxes back to the ground state and emits a photon. Because whenever you reduce energy, like jump energy like this, you are emitting some photon. Phosphorescence is a relatively slow process, and this is what causes like glow in the dark objects. Like I've got I've got a ball from my dog that glows in the dark, and the best way to use this thing is to hold it up to a lamp for a few seconds or a minute before we go out and fetching, so that it will be like really strongly glowing, and that'll peter off over a few minutes, but it'll keep glowing for like an hour, and that's because so it's because it goes through vibrational states, but it's also because your like phosphorescence flips the spin of an electron. So like if you've got like let's say you've got two electrons in an energy level down here. One of them has to be spin up, one of them has to be spin down. They cannot be the same spin because of the Pauli exclusion principle. Like a light bulb appearing slightly on after turning it off. Oh, that's actually a different. That's a different phenomenon called black body radiation. So it's basically light bulbs, at least incandescent light bulbs. They glow because the filaments are extremely hot, and it's the temperature of that filament that causes it to emit light. And so when it glows for maybe like a second or two after you turn off the lights, it's cooling down, and then it stops glowing. Keeps emitting infrared radiation for a while because it's still very warm. But fairly quickly cools off. But yeah, it's for incandescent lights at least. It is a temperature effect, and not an effect like this one. Yeah. So if you've got two electrons in this energy level here, and you excite one, and if I can't remember what conditions. What conditions this happens under, but for phosphorescence, basically you have to have the excited electron will flip its spin. So like it started here. I've got a better way to represent this actually. Let's change this around a bit. Okay, so starts off being paired, and then gets excited up to this state. So it is if the red electron here is excited and flips its spin so that it is spin up where it was spin down before, then this is what usually causes things to be phosphorescent, because it cannot just go back into this state because it's spin up, and it needs to go through other energetic states and flip its spin to get back into that ground state energy level. So I wish I remembered what processes cause an electron to flip its spin, but right now I don't, so I'm just going to ignore that for now. But basically, so in phosphorescence, this being fluorescence, and this being phosphorescence. I'm just going to change this so that it's a little more legible. Okay. Yeah, so basically phosphorescence just takes longer because it is this incompatibility of the electron spins that kind of keeps it from going back to that ground state right away. So it just takes longer to get there. And so, slowly over time, these electrons will relax back to the ground state, and when they do so, they will emit light, and that's the glow-in-the-dark effect. So, like, fluorescence stops pretty much immediately once you stop exciting electrons, but phosphorescence takes a while. So resistance wouldn't apply to this process because this is just electron energy states in an atom. Resistance happens when you have electron flow through a conductor. So like, electricity flowing through a wire, stuff like that. So that's when you'll encounter resistance. Resistance doesn't really apply here. Okay, so that was a fun tangent. Okay, last thing I will get into is this right here. So this is going to be the so this is the okay. So this is like the magnetic spin of the nucleus. And so like the direction of the magnetic field that the nucleus produces. So it wants to be perfectly aligned with the magnetic field. But it cannot be perfectly aligned with the magnetic field because that would require that the nucleus be completely stationary. And we can't have that. Nothing that has, energy is going to be entirely stationary. So like the magnetic field will in fact precess around this axis, which is in the same direction as the magnetic field. So you have basically this magnetic field just like spinning around this central point. Getting very close to it by like reaching this kind of equilibrium state where it is just effectively orbiting that axis of the magnetic field. So when very much like a spinning top. Yeah, absolutely. So when we're doing NMR, so like this state here, this kind of ordered precession. Yes, exactly. This precession around the axis here is that low energy state. And so like this is its happy place. It's now just in this kind of stable precession around this, and it's just that's where it stops. That's it's kind of ground. This is the ground state effectively for that nucleus. And then we come along and we go and mess with that. So again, these coils in the oh, I'm really glad because this is just thrown together. I am flying by the seat of my pants here, but that's okay. I appreciate the compliment. Okay, so when we want to excite the nuclear state here to this anti-aligned anti-aligned state, or actually usually we don't actually put it to an anti-aligned state. We put it to a 90-degree state. So we use these radio waves from the coils over here. It emits radio waves in a certain orientation, so that you take this stable precession of the nuclear magnetic field and you knock it to a 90-degree angle from that axis. And so like it is still precessing, but now it's precessing in like along this other axis, and which is orthogonal, or like 90 degrees to the direction of the magnetic field. And then once you stop bombarding this nucleus with the radio waves, then it begins to so then it starts to come back into alignment with the magnetic field. So its precession goes like this, and then like this, and then like this, and it gets narrower and narrower as it goes back to that ground state energy, to that stable precession. So it like goes like, I'm just not going to try that because that's just going to look silly. If we were in person, I could make this make more sense. But so you knock it out of alignment with the magnetic field, and it slowly precesses back to alignment with the magnetic field. And as it's doing that, so again, we're putting this nucleus up into an excited state, and that's this 90-degree state. And so as it relaxes back to this stable precession, it is emitting energy, and it's the energy that it gives off as the magnetic field comes back to alignment. That's what we detect in an NMR. And so this is what tells us about the kind of like magnetic information of these nuclei. Whew. So that's basically like the most basic fundamental principle of how nuclear magnetic resonance works. It's the same concept that drives MRIs in the medical field, and it is obviously just like much more complicated than this. Like I think next time I'm going to get into like what we get out of NMR and what it tells us about molecules, because NMR is probably the single most important and informative technique that we have in chemistry to get information about our about the things that we make, and we can do it about mixtures and stuff, and there's a group at my university that takes like astronaut pee and puts it in an NMR and looks at all these different metabolites, because all these molecules have different signatures in NMR that occur just through the interaction of all the magnetic fields of different nuclei, because everything affects everything else, and so there's so much information encoded into the signals that we get out of NMR. It's really pretty spectacular how much we can learn from just some squiggles on a screen. I've been going through some of that for my some of my thesis work. So we got little spectra like these and things that I've been working on and trying to annotate and make some sense of today. But the stuff I'm working with is annoying, really, sometimes deeply confusing. But it's a work in progress. But so like I use NMR like all the time in my work, and it's super important technique, and genuinely super interesting. Oh, well, thank you so much. I think it's going to be a pretty good thesis. It'll at least be it'll at least be good enough, because at this point I'm very ready to be done. Okay, so I know I may act like I'm 5, but I'm actually a pretty old man. I have been in university for more than 12 years, and I'm very ready to be done. But yeah. All right. So it has been, yeah. 12 years is crazy. Thank you so much. Like one thing I talk to my students about frequently, because like of course I talk to lots of my undergrads about grad school, and they've usually got a lot of questions, and mostly what I tell them is, if you don't super want to do this, don't, because it's grad school is a lot, and it has been one of the coolest things I've ever done. It's incredibly rewarding, and it's really necessary for me to get through to get into the kind of career that I want, which is basically like doing this stuff, teaching. But like I have to have my degrees in order to do that. But always what I tell my students is, if you don't super want this, or if you don't need this to do the thing that you super want to do, don't do it. Grad school is very stressful. It is a ton of work, and I wouldn't wish it on anybody who did not wish it on themselves. So I've been told that I have been like a significant part of several people's decision to pursue graduate studies, um, and that is very gratifying for me because I love to see my students do well and progress. But I bet you anything, I have also talked people out of doing grad studies. Because like if you don't need it and you don't want it, don't do it. Because it takes a certain amount of self-loathing to put yourself through this. Because it's tough. It's tough. The sleep deprivation can be a lot, and just the pressure to always be productive, and the constant feeling that whenever you're not working, you should be working. Um, yeah, it's a lot. It's not at all for everybody, and I always want to make sure that if people are getting into grad studies, that like it's they're getting into it for themselves, and that has to be that has to be forefront. I haven't even started my classes for BA, and I've already cried once from Phys. Yeah, that's fair. Oh, we have all been victims of physics. Yeah, physics is tough. Especially because when I started physics, I was in my first semester of university, and I get into physics, and man starts talking about, like, so you just take the derivative of this number and it becomes this one. I leaned over to my buddy. I'm like, what's a derivative? Because I had never taken calculus in high school. I learned calculus on the fly from my very kind study group that I just kind of fell into. These really lovely people like taught me the very basics of like what I needed to know to get through like the intro physics. And yeah, it was rough. Yeah, like, and then it was a semester after that I finally took calculus, and took it from a really really good professor who was just he would talk to you like you're five in the best possible way. Like broke this down into like super simple, just little bite-sized pieces. And yeah, I loved taking math from him. He was awesome. But gosh, I wish I'd done that before I got into physics. But oh well, this was the order I did things in, so yeah, is what it is. But now I have firmly forgotten almost all of that. Yeah, calculus is thankfully not something I have to do much of any of in my work because I focus on synthetic chemistry, not so much of the physical chemistry. Did AP Physics 1 was like algebraic, but never did pre-calc. Algebra 2 or basic physics, yeah. Now I do this little triangle and get the theta, hell yeah. No, we get, I just, yeah. Trigonometry is near and dear to my heart. I do love it, but, if you end up taking like university level physics or like physics that requires calculus, take calculus first. Like don't just jump into that. It's a stressful it's a stressful time. Alrighty. Well, my friend, it has been over 2 hours. I am super fried. If you're not, I applaud you. But I mean, yeah, if you are, we can do each other the kindness of calling it a night. I hope you have a lovely evening. I'll be back on Tuesday if you're around and free. I'm so fried to be so that I can fair. I love that. I may steal that. All right, have a lovely weekend. Take care and goodbye.